Hello all, welcome to the third lecture on the unit of electromagnetism. So we are today going to talk about a few different laws which are applicable in the cases of electrostatics and magnetostatics, or basically for the entire electromagnetism process. So we start with the Gauss law for electrostatics. So the Gauss law actually talks about electric flux. So what we understand electric flux is, so electric flux is nothing but it is just the total number of electric field lines which is passing through a surface. So if we consider an enclosed surface, so how many electric field lines exist in it, that is what is represented by the electric flux. Suppose we have uniform electric field and the field lines are uniformly passing through the surface, then the electric flux can be given as phi E is equal to the field vector E dot area, vector area, capital A. So phi E is equal to E dot A. Now what if the field is not uniform? Then obviously we need to consider the components of the electric field. So now the flux phi E can be written as integral of E cos phi into dA. So what is this E cos phi? It's nothing but the perpendicular or the normal component of the electric field vector. So cos phi is the term representing this perpendicular component, E into cos phi. Phi is the angle between the field vector E and the area vector A, or the elemental area A and dA, and the electric field acting on that area, capital E. Phi is the angle between these two components, E and dA. So we can in general write that for a non-uniform field, the flux phi E is given as integral E dot dA, field vector dot elemental area dA. Now, so the Gauss law can be defined as this: the flux through any surface which encloses a charge is given as the charge enclosed divided by the permittivity of free space. Ratio of the charge enclosed and the permittivity of free space, that is Q enclosed by epsilon naught. The Gauss law is given by this particular statement that the flux, the electric flux through any surface enclosing a charge is given as the ratio of the charge enclosed and the permittivity of free space. Now what if there was a charge lying outside So if there is a charge kept outside this particular surface which we have considered, then it will not contribute anything. So basically what will happen is the field, electric field lines from the charge, say if it enters the surface, then it will also go out of the surface from another side. So the flux contribution from any charge kept outside the surface will be zero. It is not going to give anything. So we are only going to get the total flux when there is a charge enclosed within the surface, and that is given by the Gauss law, that is Q enclosed by epsilon naught. So now we can represent it in integral form. So we already have that for a non-uniform electric field, the flux is given by integral E dot dA. Since it is a closed surface which we are considering, we can consider this integral as a closed integral. So if we apply the Gauss law now, we can get closed integral E dot dA is equal to Q enclosed by epsilon naught. Now this is the integral form representation of the Gauss law, a very important relation. So next what we are going to do is we make use of this integral form and get the differential form. So for that we need to bring in the Gauss divergence theorem, which we talked about in the first lecture. So if we apply this divergence theorem to this particular integral over here, we can write closed surface integral E dot dA as equivalent to volume integral divergence of the field del dot E into a small elemental volume dV. So closed surface integral E dot dA is equal to volume integral del dot E into dV. So now we can say that volume integral del dot E dV is equivalent to Q by epsilon naught, enclosed charge divided by epsilon naught. So instead of surface integral E dot dA, we closed surface integral E dot dA, we replace it by this volume integral del dot E dV. So we get volume integral del dot E dV is equal to 1 by epsilon naught into Q enclosed. And the charge enclosed, now if I consider a particular volume of the material of the surface where it is enclosed in, I can represent it in terms of the charge density, volume charge density. So instead of 1 by epsilon naught into Q enclosed, I can write volume integral 1 by epsilon naught. Instead of Q enclosed, I am going to write volume charge density rho into the elemental volume dV. So volume charge density is charge divided by the volume. So we can write charge enclosed, Q enclosed as rho into dV. So now if I just compare these two integrals, what I am going to get is, I will see that del dot E is equal to rho by epsilon naught. I just compare the integrals. So for any volume of the material, we will get del dot E is equal to rho by epsilon naught, and this is the Gauss law in differential form. A very important law, a very important equation which we need to understand the concept of electromagnetism, or even I can say to understand how electromagnetic wave behaves. Okay, so let's now move on with a simple application of Gauss law. So what we are going to do is, we now consider a spherical surface of a radius r, and let's try to find out what is the field outside a uniformly charged sphere. So this is a uniformly charged sphere, and we are going to find out what is the electric field outside this sphere. So now we bring in the integral form of the Gauss law, that is closed surface integral E dot dA is equal to 1 by epsilon naught into Q enclosed. Now what is going to happen in this particular surface is that if I consider an elemental area, the electric field and the elemental area both will be pointing in the same direction, that is towards outside. So I can write closed integral E dot dA is equal to integral mod of the field mod E into dA. So since both electric field and dA are in the same direction, the angle between them will be 0, and cos 0 is 1. So our dot product now gets converted into integral E into dA, magnitude of the field into the area. Now if the field is constant over this entire Gaussian surface, we just mentioned that it's a uniformly charged sphere. If we consider that the electric field is constant over this Gaussian surface, then we can write closed integral E into dA as, I take out the electric field outside, the magnitude of the electric field outside, since it is constant, and I just get the integral dA. Now this is a sphere, so obviously if I do the integration over the entire area, I will get 4 pi r square. So our integral now, so we started with this closed integral E dot dA. So at first we considered that E and dA are in the same direction, so the integral became integral of mod E into dA, and mod E can be taken outside because the field is constant over the surface, and integral of the area will result into the total area of the sphere, that is 4 pi r square. Now what we are going to do is replace this closed integral E dot dA by mod E into 4 pi r square. And also the total charge enclosed Q enclosed I am going to write as just small q. So I can write mod E into 4 pi r square is equal to 1 by epsilon to Q enclosed, or mod E is 1 by 4 pi epsilon naught Q enclosed by r square into a unit vector r. So instead of Q enclosed, I can even just consider as charge Q. So if this is the electric field, then we know that force acting on any charge due to this field will be just the Coulomb's force of attraction. So this actually results into the Coulomb's law. So as an application of Gauss law, we have actually derived or we have obtained the expression for Coulomb's law. Now let's now consider a case in which we have only static charges, and say I have considered a three-dimensional axis. So there are three axes, x, y and z, and I kept a charge q here at the origin, and I'm going to consider that the field is acting in this particular path. I'm going to consider a line element here, a wire. I can consider something like a wire here, and let's see what is the field acting here, say from point A to point B. So since this is just a curve, I can find the total field as integral A to B E dot dl. So that if I bring in the Coulomb's law, I can, instead of E, I can write 1 by 4 pi epsilon naught q by r square, and instead of dl, I can write dr. So what if I just integrate this particular expression? What will I get? So integral A to B E dot dl is equal to 1 by integral of 1 by 4 pi epsilon naught q by r square dr. 1 by 4 pi epsilon naught is a constant, so I kept it outside. So it becomes 1 by 4 pi epsilon naught into integral A to B q by r square into dr. So if we just integrate this and put the limits, so the distance to the point A is given as RA and the distance to the point B is given as RB, then we will get that this integral simplifies to, the value simplifies to 1 by 4 pi epsilon naught into Q by RA minus Q by RB. Now this integration is going to be independent of the path. So we can see that it is basically depending on this distance RA and RB, or the two endpoints, that is A and B, the final and the last point, initial and the last point A and B. So what if RA and RB were equal? If RA and RB were equal, we will get closed integral E dot dl as equal to 0. Closed integral, if RA and RB are equal, this entire thing gets simplified to 0. So the integral now becomes 0. So this actually proves that the electric field is conservative if we consider static charges. Now let's apply Stokes theorem to this particular integral which we have. We have closed integral E dot dl is equal to 0 for static charges. Let's apply the Stokes theorem. So if we bring in the Stokes theorem, we can write closed integral E dot dl is equal to integral del cross E dot dA. So we had discussed about the Stokes theorem in the first lecture of electromagnetism. So we already have closed integral E dot dl as 0. So if I just apply it to the Stokes theorem, I will get del cross E is equal to 0. And if I bring in the principle of superposition, that is, if we consider many number of charges, then the total electric field, as we discussed earlier in the previous lecture, we can say the total electric field is just a sum of the field acting due to each of the charges, or acting at each of the charges. So if we just apply this principle of superposition to this expression over here, we will get del cross E as del cross E1 plus E2 plus etc. or del cross E1 plus del cross E2, everything gets added up to 0. So this proves that the curl of electric field for static charges become 0, or the electric field is conservative for static charge distribution. Now let's move into get a relation between the electric field and the potential, electric potential. So we have this from the previous lecture, that the difference in potential between an initial point and final point, I can write VA minus VB is equal to integral A to B E dot dl. So VA minus VB can be also represented as integral B to A into dV, but dV is an infinitesimal change, or a small change of electric potential for a small element dl. And so I can write integral B to A dV as minus integral A to B dV. So if I, instead of VA minus VB, if I write minus integral A to B dV here in the first expression, it becomes minus integral A to B dV is equal to integral A to B E dot dl. Now since the integral limits are the same, A to B, we can write minus dV is equal to E dot dl. So both E and dl are vectors, so let's just represent them like this. Let E, vector field E, be given as unit vector I into Ex plus unit vector J into Ey plus unit vector K into Ez, and let dl be unit vector I into Dx plus J dy plus K dz. Now if we take E dot dl, we will get Ex dx plus Ey dy plus Ez dz, and that will be equal to minus dV from our previous relation. So suppose if the displacement is parallel to the x-axis, then we can consider that there is no change in y and z. So if we consider y and z as constant, then I can write minus dv is equal to ex dx, or dv is equal to minus ex dx, or hence ex can be written as minus dou v by dou x, where we have considered y and z to be constant. In a similar way, we can say Ey as minus dou v by dou y, and Ez is minus dou v by dou z. So I can now combine, I can put all these components of electric field x, y and z and combine and get the electric field vector as vector E is equal to minus of unit vector I dou v by dou x plus j dou v by dou y plus k dou v by dou z, and obviously the terms in the bracket is nothing but the gradient of the electric potential V. So we can write E is equal to minus del V, a very important relation between the electric field and the electric potential. E is equal to minus del V. Now let's apply Gauss law to this. So we already have E is equal to minus del V, and we have the Gauss law in differential form. Del dot E is equal to rho by epsilon naught. So instead of del dot E, now I can write del dot minus del V, right? Instead of E, I have written minus del V, which can simplify to minus del square V. Or I can say that del square V is equal to minus rho by epsilon naught, and this is the Poisson's equation. Now if we consider the charge density rho to be 0, the volume charge density rho to be 0, then we get del square V as 0, and this is the Laplace equation. So very important relations we have got. One is the Gauss law, del dot E is equal to rho by epsilon naught. Then we found a relation between the electric field and the electric potential, that is E is equal to minus del V. We bring in this relation and apply it to the Gauss law. We get two important equations, that is the Poisson's equation given by del square V is equal to minus rho by epsilon naught. And then we have the Laplace equation where the charge density becomes 0. So we get del square V is equal to 0. Now let's move into magnetostatics and let's try to get a Gauss law for magnetostatics. So before we get into the Gauss law, we need to understand how the flux can be represented in the case where we have a magnetic field produced. So we have considered a surface here, and dA is a small elemental area, and this black arrow represents the vector for this elemental area dA, vector dA. There is an electric field acting. These are the electric field lines which are passing through. So capital B, the vector capital B is it's a magnetic field line. So we have the magnetic field lines passing through here, capital B, and if I resolve this vector capital B, I will get the perpendicular component and the parallel component. Now the angle between the magnetic field vector B and the area vector dA is what is given as phi. So this is just similar to what we understood electric flux in the case of electrostatics. We defined it a similar way. Here also the definition comes for flux in a similar way. So the total magnetic field enclosed in the surface is what is going to be represented by the magnetic flux. So if we consider d phi b as the flux for a small elemental area dA, then obviously we need to consider the perpendicular component of the magnetic field. So the perpendicular component is b cos phi. So we get d phi b is equal to b perpendicular into dA is equal to b cos phi into dA, or in general I can write b dot dA. So it's a dot product. And if I need the total magnetic flux through the surface, obviously I integrate it. So I will get phi b, the flux, total magnetic flux, as integral b perpendicular into dA, or integral b cos phi into dA, or b dot dA. So the total magnetic flux through a surface can be given as integral b dot dA. So now let's move into the Gauss law in magnetism. So once again, so the total magnetic flux here through a closed surface is going to be 0. In the case of electric flux, in the Gauss law for electrostatics, we had a total flux resulting into a particular factor of Q enclosed by Q enclosed by epsilon naught. But here the total magnetic flux is going to be 0. So if I write in integral form, I can say closed integral b dot dA is equal to 0. Total flux is 0, so flux we just wrote it as closed integral b dot dA. So closed integral b dot dA is equal to 0, and this is the integral form for the Gauss law. So our next objective is to get the differential form for the Gauss law. So we bring in the divergence theorem, Gauss divergence theorem. So we can write closed surface integral b dot dA is equal to volume integral del dot b into dV. So if I just replace the surface integral b dot dA by this volume integral del dot b dV, I will get volume integral del dot b dV is equal to 0. Or for any volume, or if I consider the total volume of the surface, I will get del dot B is equal to 0. That means the divergence of magnetic field is equal to 0, and this is the differential form for Gauss law, a very important relation. And its physical significance, I can say that there are no magnetic monopoles. Flux through a surface is 0. That means there is always a magnetic dipole. There is always either a north and a south pole, or else a north and north, or a south and south. The poles always exist as 2. There is no monopole. A north pole cannot exist alone. There will be always the other pole coming into picture, either in the form of a repulsive force or else as an attractive force. So we need to summarize here the two important relations based on the Gauss law. So first is the electrostatics Gauss law. So that is del dot E is equal to rho by epsilon naught. But for magnetism, we see that del dot B is equal to 0. The flux is actually equal to 0. Now let's move into the next, that is the Biot-Savart law. So the Biot-Savart law basically is to express the magnetic field for a current carrying element. So we are now going to consider a wire of an arbitrary shape, say XY is the wire of an arbitrary shape, and the current passing through is given by I. Suppose the total length of this wire is L. I can divide this wire into small elements of length dl. So let me just consider a small element dl. Then the current through this element I can consider as I into dl. Now let's consider a point P over here at a distance r from this current element. And considering a point P at a distance r from the current element. The angle between the current element, the tangent to the current element, and this distance r is given by theta. The tangent to the current element and the distance to the point is given as theta. So the magnetic field which is going to be produced at this point P, which is at a distance r from the current element, is given as mu dB is equal to mu naught by 4 pi IDL sin theta by r square, where mu naught is the permeability constant given as 4 pi into 10 power minus 7 Tesla meter per ampere. I into dl is the current element which we have considered, the small current element which we have considered. Theta, as I said, is the angle between the tangent to the current element and the distance between the current element and the point in consideration, wherever the magnetic field is produced. R is the distance between the current element and the point P. So in vector form, I can rewrite this expression for magnetic field dB as dB is equal to mu 0 by 4 pi I into dl cross r by r square. So IDL sin theta is the component which you have considered. So that can be represented as dl cross r, IDL cross r. So dB is equal to mu naught by 4 pi IDL cross r unit vector r by r square. And obviously I'll get the total field if I integrate it throughout the wire, throughout this full length of the wire. Then I'll get total magnetic field capital B, vector capital B is equal to mu naught by 4 pi integral IDL cross unit vector r by r square. So just integrate throughout, you will get the total magnetic field. So that's the Biot-Savart law. Next comes the Faraday's law of electromagnetic induction. This is something which you have already learned about and even applied to electrical circuits. So this basically talks about if you have a conducting loop and if there is a magnetic field acting between the loop and say the magnet, or there is always a field between the loop and a magnet, then there is a current being induced. A current is being produced. So the Faraday's law statement can be mentioned in 2 points. First is that whenever the magnetic flux linked with the circuit changes, an EMF is always induced in it. EMF means electromotive force. And the magnitude of this induced EMF is equal to the time rate of change of the flux linked. Very important point here. Whenever there is a change in the magnetic flux in the circuit, then an EMF is induced, and the magnitude of this induced EMF will be equal to the time rate of change of the flux linked with, which we can represent as induced EMF epsilon is equal to minus d by dt, since it is time rate, rate of change with respect to time, so d by dt, and phi b is the flux, magnetic flux. So epsilon is equal to minus d by dt of phi b. Now let's try to get an integral form and differential form for the Faraday's law. So we remember this, that induced EMF epsilon is equal to minus d by dt of the flux, magnetic flux. So let's consider a conducting loop. So this is the curve representing the loop. We have the curve representing the loop. We have a small element dl, and we consider the point P here. There is an electric field acting outward. And let's have a small elemental area dA within this loop. And we have the magnetic field acting over here at that elemental area. So suppose if the surface has a magnetic flux which is uniform, then we can write the induced EMF as epsilon is equal to closed integral E dot dl. The induced EMF produced can be written as closed integral E dot dl. So we are considering this electric field vector and the elemental line dl. So that gives the induced EMF. So if we put this into the expression for induced EMF which we just talked, we can say that instead of epsilon we put the integral, so it becomes closed integral E dot dl is equal to minus d by dt of the magnetic flux. And this is the integral form of the Faraday's law. Let's get the differential form. For that, we need to bring in the Stokes theorem. We have to apply the Stokes theorem. So Stokes theorem says closed integral E dot dl is equal to integral integral curl of E dot dA. So instead of closed integral E dot dA, we are going to get integral del cross E dot dA. So we can write integral del cross E dot dA is equal to minus d by dt of the magnetic flux. So magnetic flux, we just talked some time ago that magnetic flux is nothing but integral of the magnetic flux through the surface. So phi b can be written as integral b dot dA. Phi b is integral b dot dA. So let's just substitute for the phi b in the previous expression. So we will get closed integral del cross E dot dA is equal to minus d by dt of b dot dA. Okay, sorry, there is an integral over here. Minus d by dt integral b dot dA. Or I can write minus d by dt integral b dot dA as minus of integral dou b by dou t dot dA. Minus integral dou b by dou t dot dA. If I take the total differential inside the integral, it becomes partial. Now this is same for any area of the total area if we consider. So we can write del cross E is equal to minus dou b by dou t, and this is the differential form of Faraday's law. So in this particular lecture, we have actually talked about Gauss law in electrostatics and then in magnetostatics. So we got Gauss law as del dot E is equal to rho by epsilon naught, and that is the divergence of electric field. The Gauss law from magnetism says the divergence of magnetic field del dot B is equal to 0. The Gauss law in electrostatics we use to get two important relations, that's the Poisson equation and the Laplace equation. Then we made use of the concept of the magnetic flux, and we talked about the Biot-Savart law, and then we got the Faraday's law. We made use of the concept of Faraday's law of electromagnetic induction, where an induced EMF is produced when there is a change in the magnetic flux. So we got the Faraday's law in both integral form and differential form. So all the differential forms, that is divergence of electric field, divergence of magnetic field, and the curl of electric field, which comes from this Faraday's law, are very important. And now we are left with the curl of the magnetic field, which we will come across in the next lecture. Thank you.